So they do form compounds, okay? And their compounds, if you are to compare the group 1 and the group 2, these group 1 compounds, they are more ionic than their corresponding group 2 elements. And why? It all goes back to the polarization power. In that, in group 2 elements, since they have more, their charge is higher and their ionic radius is low, they will have a more polarizing power, okay? Whereby they will highly polarize their compounds. If they are carbonates, they will highly polarize the carbonates. If they are chlorides, they will highly polarize the chlorides, making their compounds to be less ionic, okay, as compared to their corresponding group 1 elements. And so the reason is you have a low charge density in group 1 elements, okay, and so because of that low charge density, it makes them not to polarize their compounds. Is that okay? So the salts of group 1 elements, their salts, the salts of group 2 elements, they are less soluble in water than those of group 2 elements. For instance, if you are to check the sulfates, okay, if you consider maybe potassium, okay, and calcium. Now potassium sulfate, it is highly soluble, but calcium sulfate is sparingly soluble. If you consider hydroxides, okay, potassium hydroxide is highly soluble, okay, but calcium hydroxide, it is insoluble, okay. So there, if their elements, their compounds, the salts of group 2 compounds, they are less soluble as compared to their fellow counterparts in group 2. Why? You should be in position to explain that. And good enough, we studied the physical chemistry, you remember that. And we say that the solubility of these salts depends on hydration energy and the lattice energy. Now, for group 1 elements having a small charge, so that a small ionic radius, they have a high lattice energy, okay, that cannot easily be outweighed by the hydration energy, okay. And so if the hydration energy is small to outweigh the lattice energy, then the solubility, the enthalpy of solution of such a compound is going to be positive, which makes it less soluble in water. Is that okay? Yes. So good enough, I think all of us here know what lattice energy, what is enthalpy, what is, so we now know what these ones mean. So you can see the solubility of any compound is affected by the lattice energy and the hydration energy. I.e. soluble salts, they do have a negative enthalpy of solution, and this is what we've been covering. So the more the negative the enthalpy, the more the solubility of a salt. So if your lattice energy, okay, for group 2 for instance, with the lattice energy that is high because of their sizes, the lattice energy is going to be high, okay, that it won't be easily outweighed by the hydration energy. So as a result, the salt will dissolve with absorption of energy, which we call endothermic. But if the salt has less lattice energy, for example, for the group 1 elements, they have a large size, okay? So the ionic bond between the crystal lattice, the crystal, the elements, okay? Maybe if it is sodium and then the chloride, the bond won't be that big, won't be that strong, that you can easily hydrolyze that bond. You can easily break that bond, okay? So the energy needed to break the bond is not that much, okay, that it can easily be outweighed by the lattice energy. Hence the solubility of group 1 elements and group 2 elements is going to vary in that manner. Okay? Yeah, that's brilliant. Now for hydrated salts, we also talked about this in physical chemistry. If you attended our previous lesson, we saw that the hydrated salts. What do I mean by hydrated salts? For example, if I say copper 2 sulfate, copper 2 sulfate, 10 water, okay, 10 water or 5 water or something. So it can't write a dot. Let me do this. So this one is a hydrated salt. Why? Because it has this water of crystallization. But just copper 2 sulfate, now this is anhydrous. It doesn't have any water of crystallization. So the hydrated salts, they do dissolve endothermically. You apply some heat for it to dissolve. Whereas anhydrous salts, they do dissolve more exothermically with evolution of heat. Why? We explained this, but to repeat, the reason is simple in that for you to dissolve, the lattice energy, the hydration energy must outweigh the lattice energy. But now see, this is a hydrated salt where some of the ions, the copper 2 ions, the copper 2 ions and the sulfate ions are already surrounded by the water molecules, these ones. Okay? So they are partially hydrated already within the salt. So, for you to dissolve it, you need relatively high energy to break the crystal lattice, that is the lattice energy, than the energy that is going to be given out when the gaseous ions are surrounded by the water molecules. So as a result, the hydration energy is going to be too little to outweigh the lattice energy. And so you dissolve with absorption of heat, or you need to apply some heat externally to dissolve such a salt. Okay? Yes, that is basically the reason. So they dissolve exothermically. Why? Why? My pointer. The hydrated salts are already partially hydrated. And so what does that mean? The hydration energy won't be is lost. Somebody is calling me. So the hydration energy is lost. Thus, when the crystals are dissolved in water, this hydration energy is not enough to outweigh the lattice energy. And so they will dissolve with absorption of heat. But for anhydrous salts, the hydration energy is enough. Why? Because the ions, the gaseous ions, are not surrounded by water molecules. So the energy that will be evolved, the energy that will be lost when they are surrounded by the water molecules is going to be high enough to outweigh the lattice energy, hence dissolving exothermically. As simple as that. Is that okay? Yes, in case you have a question, you can drop it. So, for instance, you can check on that. This is what we've been studying, and we shall not repeat this. You have a salt, and the salt is AX, and the hydration energy here, it is 880, and the lattice energy here, it is 860. So now, these values, they are negative. The hydration energies, they are negative values. But these ones, they are positive values. So what does that mean? If you are dissolving this salt AX, since this value, the hydration energy, is higher than the lattice energy, as you can all see, okay, and the enthalpy of solution is going to be, enthalpy of solution is going to be minus 20. And since our enthalpy, kilojoules per mole, okay, kilojoules per mole. And since our enthalpy is negative, then this salt is going to dissolve with ease, this AX. But now with this one, whose enthalpy of hydration is less negative, is less than the enthalpy, the lattice energy, okay, then this salt is going to dissolve endothermically with absorption of heat. A moment, guys, just a moment. So the question is, state which salt is more soluble and explain your answer. And all of you should be in position to see that salt AX, okay, is more soluble. Why is it more soluble? Because its enthalpy of solution is negative, okay? It has a negative enthalpy of solution, kilojoules per mole. But for salt BX, okay, it's less soluble because if you take its enthalpy, okay, its enthalpy, which is that is plus 10 kilojoules per mole, it is less soluble compared to salt AX. So if you dissolve, maybe if you have your 100, how do we measure solubility? If you have your 100 centimeters cubed of water, okay, at room temperature, which is 25, okay, degrees Celsius, and you dissolve both these salts to make a saturated solution. A saturated solution is that solution which cannot dissolve any more solute, okay, for both AX and BX. And then if you try to determine the concentration of AX in 100 grams of water and the concentration of BX in 100 grams of water, you find that AX has more concentration, okay, in 100 grams of water than BX. So that's what we mean by the solubility of this is going to be higher than the solubility of this. However, all these salts they are soluble. Why? Because their enthalpy of solution is less than the room temperature, as you can see. However, this one, it dissolves exothermically, so it's more soluble than this. Is that okay? Yes. Any queries? Let me check for your queries. It's inevitable. You have to talk to the neighbors. You can't live alone. You have to talk to the neighbors. Okay? Yeah, so that's why. So now with these hydroxides, okay? Obviously they are all white substances. Why? Because the cations, the group 1 and group 2 elements, they are not colored ions. Okay? And obviously they will all appear white. All of them. Both for group 1 and group 2 elements. They will all appear white. And they are deliquescent. What does that mean? Deliquescent, it means they do absorb water vapor from atmosphere to form either a solution or you don't form a solution. Now that is hygroscopic and deliquescent. You can find out their differences. But they can all do absorb water from atmosphere. That's why when you are given any sample, okay, when you are given any sample and it's a white sample, always cover it. Otherwise, if you don't cover it, you start with a powder or with some crystals, and by the end of the practical, you have a solution. And then you wonder, how am I even going to heat this solution? Yet, sometimes it is encouraged to do the heating after. So that after you have a clue, you have a hint that I have this, and I have this. So, if I have this, I'm expecting to see this, and to see this, as far as heating is concerned. But still, you can also do the heating before to give you a clue, okay, of what you are expecting. So in other words, there is no harm if you heat both at the start and at the end. Okay? So now, but at the end, For you have just left your sample exposed in air. Okay? The question is, what are you going to hit? Are you going to hit a solution? For us, we want you to hit a dry sample in a dry test tube. So what are you going to hit? So that's why you should keep them covered. So they are deliquescent except lithium hydroxide. For lithium, remember the diagonal relationship, okay, of this lithium. It tends to misbehave from others. So they do dissolve in water exothermically to form strong alkaline solution. All group 1 elements, all group 1 hydroxides, they dissolve in water. Apart from, now for the group 2, for them they have a lot of English, okay? Their solubility decreases down the group, okay? That's why magnesium hydroxide, it will tend to, however, it is also insoluble, okay? Calcium the same, barium the same, strontium the same. Actually, it is strontium which I was looking for. The same. But for group 1 hydroxides, for them they readily dissolve. Okay? You look at sodium hydroxide. Look at potassium hydroxide. Look at rubidium hydroxide, cesium hydroxide. So they readily dissolve. Why? It still goes back to the lattice energy. Okay? Lattice energy. Good, we have studied this after studying thermochemistry. So dissolving, that is enthalpy of solution. Now for group 1 elements, their lattice energy is going to be low. Okay? That the hydration energy will easily outweigh it. Why? Because they have large sizes. Even the solubility is going to increase down the group. The solubility of these hydroxides, it is going to increase down the group. Why down the group? Because down the group, the atomic radii increases. So their sizes increase. And if the sizes increase, what does that mean? The lattice energy, the ionic bond joining the two between the OH and the metal, okay, is going to be weak, so you can easily break that bond. So the lattice energy won't be that pronounced, but the hydration energy, the heat that is evolved when these ions are surrounded by the water molecules, is going to be high. Okay? And so if it is high, then it will outweigh, okay, the lattice energy. Hence the hydroxide, the salt, becomes more soluble as you go down the group. So organic chemistry is all about that. No, in organic chemistry, I mean, it is all about that. I'm able to explain a given trend. If you can't explain a trend, then life becomes hard as far as inorganic chemistry is concerned. Is that okay? Yes. Now for group 2 hydroxides, like I said, they are sparingly soluble and they are prepared by precipitation therefore. What do we mean by precipitation? With the precipitation, I mean you mix two soluble salts to form an insoluble salt, and then you separate it by filtration, and then you dry it. For instance, assuming I want to prepare maybe, okay, calcium hydroxide, okay, calcium hydroxide. So there is, oh my god, okay, calcium hydroxide. So assuming I want to prepare this OH. Now this one, it is insoluble in water, okay? It is insoluble in water. So what am I going to do? I'll get my two solutions. One solution will have the calcium ions and another solution will provide the hydroxide ions, so that when they two come together, they will form that insoluble salt. And that's what we call precipitation. And for instance, the solution maybe I can decide to use calcium nitrate or calcium chloride. Those ones, they are soluble. Maybe let me use calcium chloride. Okay. This one is soluble, aqueous. And so from calcium chloride, I can decide to mix it with any solution that will provide hydroxide ions. Maybe you can guess. Oh my god, sorry for this. Maybe it can be sodium hydroxide. I can use sodium hydroxide, I can use potassium hydroxide. Okay, and this one is an aqueous solution. And so when the two combine, or when the two react, I'll form my calcium hydroxide. Okay, and this is my insoluble salt. Okay, and this is a solid plus what? Plus my sodium chloride, and this is a soluble salt. Okay, sodium chloride, and then this is aqueous. Now for me, my interest is calcium hydroxide. So what am I going to do? I'll either decant, I'll leave it to settle and power off this layer, this liquid, this solution, and I remain with calcium hydroxide at the bottom. And then I dry it off, and I keep it as calcium hydroxide. Alternatively, if I have no time, then I'll get a filter paper and filter the whole of this solution. Okay, and if I filter this, then I'm going to have my filtrate as this, and the residue within a filter paper as this, and then I dry the filter paper, I dry the residue and store it. So depending on whatever is needed, you can maneuver it. Okay? Yes. So that's what we mean by precipitation, where you mix the two soluble salts to form one insoluble salt. However, the beryllium hydroxide cannot be prepared by this method. Why? It will form a complex. Since beryllium has a high polarization power, okay? It has a high charge density, so high. So its polarizing power is so high. When you do that, yes, it will form that insoluble hydroxide, okay? Insoluble hydroxide, which is BOH, and then with a 2 here. But since the OH is going to be excess, since the sodium hydroxide is going to be excess, then it will further react to form a complex, which is Be, then OH, and then 4. And this is 2. Is it 2 minus? Yes, 2 minus. Now, this is a complex, yet for you are interested in a salt. So it becomes hard for you to get what you wanted. So, with beryllium, we cannot prepare it using this method. With beryllium hydroxide. Is that okay? That's pretty good. That's brilliant. That's brilliant. So then how do we? We prepare it by dissolving a normal oxide of beryllium in water. So you just get beryllium oxide and you dissolve it in water, you produce your beryllium hydroxide. So now, question, explain why beryllium hydroxide cannot be prepared by precipitation method. It's what we have just discussed. Being an amphoteric hydroxide, it means it can dissolve in both, it can react with both alkalis and acids. It cannot be prepared. It will further react with OH ions to form what we call a complex, the tetrahydroxyl berylate 2 ions. The solubility of hydroxides of group 2 elements. You can see from this, you can tell that the solubility, does it increase or decrease? From 0, it is increasing here, increasing. Let me take off this. It is increasing. So the solubility is increasing down the group. Which explanation can you give? Which explanation can you give? From the figures, we can see that the solubility increases down the group. It's simple. It goes back to the lattice and hydration energy. So as you down the group, the sizes keep on increasing of these group 2 elements. Okay? They from beryllium to magnesium, the size does increase. To calcium, the size does increase. To strontium, to barium, the same thing. The size does increase. So the increase in size, therefore, decreases the lattice energy. And if you decrease the lattice energy, then what does that mean? The hydration energy will outweigh the lattice energy, which will lead to an increase in the solubility of a given hydroxide. Is that okay? Yes, now let me check the chat box. You never know. Some people might have questions for me. So, the increase is due to the radius. You can see it is decreasing. The charge density, it remains the same. However, the lattice energy is going to decrease, okay, more than the hydration energy. So due to the small size of the hydroxide ion, the lattice energy decreases more rapidly than the hydration energy. Therefore, the enthalpy of the solution becomes negative. Maybe you might not get this the way you want. So it is maybe okay. Let me use the way they are. So you have beryllium, you have magnesium, okay, you have calcium, you have strontium, and you have barium. Okay. Now all these cations, as you go down the group, their sizes are increasing, okay, and their radii are also increasing. Anyway, their sizes are increasing, but the charge remains the same. So therefore, the polarizing power, that strength of the ionic bond, is going to decrease, okay, down the group. However, for hydration, yes, the OH remains the same. The OH remains the same. Even here, the OH remains the same. So, since the OH is the same, the decrease in the lattice energy is going to be prominent. There's going to be a high decrease in lattice energy because the cations are decreasing, the bond is weakening, and so the lattice energy is reducing. A moment, guys. So you keep unmuting, yeah? Or let me see if I can edit from here. So since the lattice energy is decreasing, the decrease in lattice energy is more prominent than the decrease in hydration energy, then the hydration energy is going to outweigh the lattice energy, hence making, okay, your salt to be soluble, hence making the solubility to increase down the group. I hope it has been explained regardless of the interruptions. I hope you can. So if it's not okay, you can come to me. Now for the sulfates, it is the reverse. The solubility for it decreases down the group. You can see beryllium highly soluble, magnesium relatively soluble, calcium you can check on the solubility, strontium insoluble, and barium sulfate insoluble. Now, why is it decreasing? It still goes back to the lattice energy and hydration energy. If you understood those concepts right from physical chemistry, okay, then you can easily explain. Because for you to dissolve, the enthalpy of solution must be negative. And the enthalpy of solution is dependent on the hydration energy and the lattice energy. Whereby if the lattice energy increases and the hydration energy decreases or cannot outweigh the lattice energy, then the enthalpy of solution becomes positive, and so you need energy, the solubility decreases. But however, if the hydration energy is negative and the lattice energy is relatively lower than the hydration energy, then the enthalpy of solution becomes negative and the solubility increases. If you understand that concept, please, you should not fail any question concerning explain the solubility in group 1, group 2, group 3, group 4, group, any period. Solubility is dependent on these concepts. Not so? Yeah, that's brilliant. Let me get, I don't need this. Oh, anyway, it will disturb. So this is due to, the decrease in ionic radius of the cation. Since the sulfate ion is large, okay, since the sulfate ion is large, there is some science here, then the hydration energy decreases more rapidly than the lattice energy. Therefore, the enthalpy of solution becomes less exothermic. There is something I want you to, and the trend here is the same for carbonates, for chromates, for phosphor, this is phosphates, and then for chloride. But for hydroxide, it is reverse. Okay? So now, in your mind right now, can you explain the difference in solubility of hydroxides of group 2 elements and hydroxides and carbonates of group 2 elements? Can you really give a detailed account, a detailed explanation for the observed difference? Maybe let me just give it a wrap up. So if we talk about the observed difference in hydroxides, okay, in OH and in carbonates for group 2 elements. Now what is differing? It is hydroxides and carbonates. But the group 2 elements, they remain the same. So if it is beryllium, you have beryllium here, which does it even exist? There is minus here. You have magnesium, you have calcium, you have strontium, and you have barium. But for hydroxides, you have the same beryllium, magnesium, calcium, strontium, and barium. And the question says, explain the trend. Okay? Explain the solubility in group 2 hydroxides and group 2 carbonates. So the difference becomes this. For the hydroxides, the solubility decreases, so they increases down the group. However, they are also sparingly soluble. They are not that soluble. But for carbonates, sulfates, chlorides, now leave chlorides alone for that reason. But for carbonates, for sulfates, the solubility decreases down the group. Okay? Yes. Here, down the group, we have seen that the lattice energy decreases so much. Why? Because the sizes of these atoms, these elements, is increasing. But since the OH, you see you have oxygen bonded to the hydrogen. So since the OH is a smaller ion compared to the carbonate, compared to the sulfate, compared to the chromate, compared to the phosphate, the OH is going to release too much energy when it is surrounded by the water molecule. That this much energy, coupled by the decrease in the lattice energy down the group, okay, it will lead to an increase in solubility. The enthalpy of solution will become relatively more negative. But for carbonates with a large size, okay, the lattice energy, okay, yes, there will be a decrease in lattice energy, okay, but the decrease in hydration energy is going to be much more pronounced, okay, than the lattice energy. Remember this one, they are also increasing, so the hydration energy decreases so much. Even here, the size, yes, this one remains the same with smaller lattice and with smaller hydration energy. So as a result, the enthalpy becomes more negative, okay? So the lattice energy becomes much, and so the enthalpy of solution becomes more positive, which leads to the decrease in solubility as you go down the group. So if you can explain that, if you can write an essay to explain these two, okay, the differences in solubility, then you'll be good to go. Is that okay? Yes. Let's talk about carbonates and hydrogen carbonates. Now for
I'm
carbonates,
begging for pardon.
pardon, somebody said something. Did you want the hydrogen carbonates? Now, the group 1 carbonates, let me get some pen here. For the group 1 carbonates, they are all soluble and they are stable, okay? Except the lithium carbonate. Why lithium? You know, the diagonal relationship. Too small, high charge density. So it greatly polarizes the carbonate that it cannot, it will become more of a covalent. It will form a covalent bond than an ionic bond. And so that covalent bond cannot dissolve in the water. But other carbonates for the group 1, they are highly soluble. Talk about sodium carbonate. Talk about potassium carbonate. Okay? Talk about cesium. Okay? Is it CS or yeah, it's CS. Talk about rubidium. So as you go down the group, the solubility of these carbonates keep on increasing. Okay? Yes. And the thermostability by them, they also become stable. Okay? Why? Basing on the ionic bond that is formed. So therefore, since they are stable enough, then how are we going to prepare them? Unlike the group 2 carbonates, we shall prepare them by bubbling carbon dioxide through any hydroxide solution. It could be lime water, okay? It could be calcium hydroxide, any hydroxide solution. Or if you know, actually, so any hydroxide solution, it could be sodium hydroxide, it could be calcium hydroxide, potassium hydroxide, commonly these ones, after we are preparing group 1. Okay? And what happens when you bubble? We shall form the precipitate, and the precipitate is going to be a hydrogen carbonate. Somebody has joined? Or I think somebody has joined. Oh, I've lost connection. Let me check. Could be the reason. Let me check. What happened? What happened? I lost connection. So for the carbonates, we shall prepare the carbonates of group 1 by bubbling carbon dioxide, okay, in any hydroxide solution. And then if you bubble this, then we shall form a low soluble hydrogen carbonate. Okay? Now if you bubble this, you form a carbonate. Now there is this senior 3 science that you studied about the carbon and its compounds, the carbonates. Where let me first get some space to distinguish between calcium carbonate and sodium carbonate. Where if you have carbon dioxide, maybe let's first talk about this in details. If you have carbon dioxide and you bubble it in sodium hydroxide, okay, if the carbon dioxide is little, okay, then we shall form sodium carbonate, and the sodium carbonate is soluble, okay, sodium carbonate plus water, so on. But my aim is on sodium. Anyway, let's write plus water. And this carbonate is soluble. And the same occurs with calcium hydroxide, the lime water. Okay? Calcium hydroxide. Also, if you bubble there a little carbon dioxide, this is 2. Don't mind about the states. And you bubble there carbon dioxide, still we shall form calcium carbonate. Now for calcium carbonate, this was senior 3 science. I don't know if you were told about it. For calcium carbonate, for it is insoluble. Okay? Plus water. And this calcium carbonate is formed when you bubble little carbon dioxide. Okay? But now, even here, little carbon dioxide, we shall form a carbonate. And in this case, it is sodium carbonate. And in this case, it is calcium. However, this one is soluble. And this one is insoluble. Now, when we bubble in excess, okay? Now, in excess, okay? You bubble in carbon dioxide in excess, okay? In sodium, sodium carbonate. I think there is a 2 here. I think we need to add some water. We shall form sodium hydrogen carbonate. And this one is insoluble. Whereas here, if you bubble excess, okay, we shall also form calcium hydrogen carbonate. Okay, calcium hydrogen carbonate. And now this one is soluble. So those are the 2 different observations. With sodium hydroxide, we shall form, if you bubble excess, no observable change. But if you bubble little, no observable change. But on excess, a white PPT is formed. But with lime water, if you bubble little, the solution turns milky. White PPT is formed. But on excess, turns colorless. So that was the observation. So now also here, if you want to prepare sodium hydroxide, then we shall add excess carbon dioxide. Did I say sodium hydroxide? Sodium carbonate. We shall add excess carbon dioxide in sodium hydroxide to produce the precipitates of sodium hydrogen carbonate. Now, since carbonates of group 1 are stable on heating, then we shall try to decompose our hydrogen carbonate. And when the hydrogen carbonate decomposes, it forms sodium hydrogen carbonate. It decomposes to form the sodium carbonate. And now, this is our sodium carbonate, okay, plus the water, I think. So this is our sodium carbonate that we want, and that's how we shall prepare the carbonates of most of the group 1 elements. Okay? Yes, I hope this one is okay, and I'm going to erase everything. So that's how we prepare them. But for group 2 carbonates, for them they are prepared by precipitation. There is this one. Lithium. Explain why lithium carbonate is insoluble in water. You can explain this. Having a small ionic radius with a high charge, it will have a high charge density, which will end up polarizing the carbonate ion, turning a bond into more of a covalent bond. And covalent compounds cannot dissolve in water, so it will end up becoming insoluble. Not so? So that is the reason. But now for group 2 carbonates, I think I have them here. I should have them. Describe how sodium carbonate can be prepared by the Solubility process. On a large scale, it is the same that we have just discussed. Now for group 2 carbonates, since they are insoluble in water, they will be prepared by thermodecomposition, by precipitation. I said this, okay? But however, you cannot prepare them using the same way. They can, if you heat them, unlike for the group 1 elements, which you're going to heat the sodium hydrogen carbonate to form the sodium carbonate. Unlike the group 1s, for them they can decompose to produce carbon dioxide gas and the metal oxide. Okay, so you can't prepare them in that same way. So the easiest way of preparing them is by precipitation, whereby you get a soluble right just up here. You get any solution that will provide the carbonate ions, okay? Any soluble salt, any soluble carbonate. Maybe you can use sodium carbonate, potassium carbonate, and so on, okay? And you dissolve it in water to give you the carbonate ions, and then you get any group 2 metal ion solution. Maybe it could be a chloride, it could be a nitrate, okay? And so when you react them, we shall get our insoluble carbonate, which is M carbonate, where M is a group 2 element, and this is a solid. So where M, it can be, okay, let's say beryllium, it can be magnesium, it can be calcium, it can be strontium, and M can also be barium. Okay, so I hope that one is okay. I hope this one is really okay. So any question as far as this is concerned? In case you have a question and the question is immediate, feel free to drop it in the chat box. I'll be happy to attend to your question the way it is. Now for group 1, like I said, they are stable to heating. The group 1 carbonates, they are stable on heating, okay? They have very high melting points, very high boiling points, so they cannot just be decomposed. And the high melting point, the high boiling point is due to high lattice energy, okay? The stability of ionic compounds depend on the standard lattice energy, okay? And the lattice energy, like I told you, it is that energy required to break down a crystal lattice, okay? And so the higher the lattice energy, the higher the energy required to break such a crystal lattice, and so the more stable a compound is, okay? And the lattice energy will depend on the following. We discussed this several times: the ionic charge, the number of electrons that are used or that are contributed to the formation of an ionic bond, the higher the electrons, okay, the higher the number of electrons, the stronger the ionic bond that is going to be formed, and so the higher the lattice energy. And also the ionic radius of both ions, not one. If the ionic radii of both ions are high, then it means these ions, they will strongly attract each other, and so the bond that is going to be formed between the two ions is going to be so strong that it cannot easily be broken. And so as a result, if the bond is strong, then you need relatively high energy, so much energy, too much energy to break such a bond, hence a high lattice energy. So we have almost discussed all this. So if the question wants you to explain the solubilities, you should be in position to give. If the question wants you to explain maybe the thermostability of carbonates, sulfates, the variation in the melting points, boiling points, all that. And inorganic chemistry is about that. That's why it's one of the easiest branches. Okay? It's just about that. Explain this, explain that, explain this, explain that, and the concept will always be the same. Those periodic properties that we talked about, okay, they are the ones that work here. Because you have seen, we are explaining lattice energy, and what is affecting lattice energy? Ionic radius, charge density, blah blah blah, and so on. And what is affecting lattice energy, by the way? You know the factors. You know how we've been doing it in physical chemistry, where you start with atomization energy. The factors which affect the atomization energy, it is how much the atoms, how the metallic bonds, the strength of the metallic bonds, because you are breaking the metallic bonds to convert the individual atoms into gaseous atoms. So that one will affect. Then after that, you go to ionization. So the energy, how strong the outermost electron is bound onto the nucleus, will determine your ionization energy. Okay? Then from that you go to electron affinity. Depending on the need of the incoming electron, it will determine, okay, how your electron affinity is going to be. Then after electron affinity, then you go to lattice energy, the two combining. So the magnitude, the strength of the lattice energy, it will depend on those factors, the atomization, ionization, and electron affinity. And ionization energy, we studied them in periodic properties. So if those periodic properties are good, then you can relate any concept. Okay? And so if you can relate any concept, then you'll be good to go for both physical, inorganic, and organic chemistry. You'll be an all-around student. Okay? Not this student who'll be like, me I want to do physical alone. Me I want to do, no. Be an all-around. I don't want to talk about any. Let me leave this. But be an all-around student. Okay? Good. So let's talk about the nitrates. The nitrates of group 1, obviously they do decompose to nitrites and oxygen, except for lithium, which decomposes to an oxide, nitrogen gas, and oxygen gas. So you can write an equation. Group 1, let me say, let me say for example sodium, sodium nitrate, and this is a solid. It will decompose to give us sodium nitrite, and this is a solid, to oxygen plus oxygen gas. Okay, so if you try to balance, how should we do it? So if you put a 2 here and a 2 here, is it balanced? Yes, I hope it is. 6, 6, yeah, it is balanced. But for lithium, then we shall form lithium nitrate, okay, lithium nitrate, and it's a solid. For it will decompose fully to give you the oxide, lithium oxide, and it's the solid, plus nitrogen dioxide gas, okay, and finally the oxygen gas. Okay, now if you try to balance the oxygens we have, if you put a 2 here and a 2 here, I think it will be balanced. Is it, this is 6 oxygen, we have 6 this side, then so we have 3, so we have 4 plus this is 6. Oh, it's not balancing. Okay, so if we put a 4 here, shall we manage? Anyway, let's save time. You will balance it. You're going to balance this. Okay, you balance that. So that is for group 1 elements. Their nitrates decompose on heating to give you this. Now so we have an explanation. Explain why sodium nitrite is more stable than the sodium nitrate. So why are we decomposing from sodium nitrate to form the sodium nitrite? Why? So it is simple. The sodium nitrite, the nitrite ion, has a smaller, or is smaller relative to the nitrate, and thus forms a stable ion. The lattice energy is going to be high, that you relatively need high energy to decompose, to break the lattice energy between the nitrite and the nitrate. Okay, hence the sodium nitrite becomes more stable compared to the sodium nitrate. Now for group 2 elements, so we have an equation before what is there, but anyway, for group 2 they do decompose to give us the metal oxide, the nitrogen dioxide gas, and the oxygen. And the oxide being smaller and the oxygen being highly electronegative, okay, it will be formed, it is more stable, so the nitrate will decompose to produce the oxide. So therefore the nitrates of group 2 decompose to a metal oxide, nitrogen dioxide, and the oxygen gas. And the equation is here. For example, magnesium nitrate, magnesium oxide, nitrogen gas, and the oxygen gas. So you should be in position to write that equation with ease. For the carbonates of potassium, sodium, rubidium, cesium, they are stable and do not decompose. Okay, explain why lithium carbonate decomposes. It polarizes. So the bond between the lithium and the carbonate, it is roughly covalent, whereas other elements, the sodium, the potassium, the rubidium, the bond is purely ionic. Okay, and the compound, the carbonate, is purely ionic, and so ionic bond is strong compared to a covalent bond. Okay, so it does not easily decompose. But for lithium carbonate, it will easily decompose. So lithium ion have a high charge density. So this is, we've been talking this. Hence easily polarize the carbonate to form a covalent bond which held by weak van der Waals forces of attraction, making it easily decompose. Why sodium carbonate is used as a base in acidic titration? Because it is stable. And then state and explain what is observed when sodium carbonate solution is added to aluminium chloride. I won't answer this now, okay? But we shall find it down, okay? We shall answer this now. I shall not answer this now, but we shall find it down when we are studying beryllium. I think it is the next question. And then we shall talk about it some other time when we are talking about the group 3 elements. Okay? Yes. Write the equation of reaction in this. This very quick. We want this equation. Still, we shall find it down. Group 2 carbonates. That's how their boiling points, their melting points is varying. This one boils at 100, increases, and these ones, they are so high. You should be in position to explain that. In case, by the way, in case you cannot explain this, it's okay. Maybe let me check the chat box for the concern. So if you've been attentive right from where we began from, this should be a walkover. Okay? Yes. Complex formation. Now, this is where the question is coming from. Now, for group 2 elements, they are able to form the complex ion. Actually, not all of them, but beryllium. Okay? As you can see, beryllium is able to form complexes. Why beryllium? Because if you are to compare its charge density with other elements, okay? If you are to compare its polarizing power with other elements in group 2, it is high. It's high. Okay? For you to form complexes, you must have a high charge density to attract the lone pair of electrons in the other ligand. Okay? For example, if you react maybe beryllium with excess ammonia, okay? Excess ammonia, let me write 3. The nitrogen having a lone pair, the beryllium must be able to attract this lone pair towards itself and hold the lone pair on itself. Okay? You should be able to attract so that you form your beryllium ions or tetra amino. So this is NH3 and then 4, okay, and then 2 plus, so that you are able to form this complex tetra amino beryllium 2 ions. You must be able to strongly attract the other lone pair. It's like for you agreed. They give you your food, you eat it, then your neighbor who is not good at eating, you also get his food and eat the whole of it. Okay? So you attract yours, but also you receive electrons from your neighbor and you also attract the electrons. Okay? So that's when you'll be able to form the complex. Also, another factor is you must have where to accommodate the electrons from, the lone pair of electrons from. Okay? So presence of the empty orbitals. Okay? And within the group 2 elements, this is their outermost configuration. If this is your neon, okay, then you have the 3s2, okay, and here you have the p orbital, and this p orbital is totally vacant. It's totally empty. So it is in this p orbital where the lone pair is going to be accommodated, okay, during complex formation. Otherwise, if you don't have where to put the electrons, then you cannot form the complex. So presence of the suitable vacant orbital to accommodate the lone pair of electrons from a ligand to form a dative bond. And I hope we talked about dative bond in bonding. Okay? And if you have to check on beryllium, it has all these factors. Okay? And so it is able to form the complexes. Okay? So down the group, the tendency to form complexes decreases due to decrease in charge density. And so you cannot hold the ligands onto yourself. But for beryllium ions, having a high charge density and having that empty p orbital, then they can easily form complexes. That's why you have complexes such as beryllium tetra. This is tetra aqua because this is water. So tetra aqua, beryllium 2 ions. Tetrahydroxo, not hydroxo. Tetrahydroxo, beryllium 2 ions. This one, tetrafluoro, beryllium 2 ions. So you are able to form complexes. Why? Because of that small charge. Okay? Then you can easily accommodate the electrons from these donor ligands, and since you have where to donate the electrons to, then you can easily form complexes. Is that okay? Yes. So I don't know if you guys are still sober. Recording. So it's okay, it's okay. So for hydrolysis, like I said, it's a reaction where a salt reacts with water, which results into a change in pH. And I was saying that if the pH, instead of it being neutral, becomes slightly acidic or neutral. And it is for hydrolysis to occur, it occurs within the smaller ions, okay, that can easily polarize the water molecule to react with it. But for salts of large ions, for example, within group 2 and group 1, if you go down the group, the tendency to polarize, the tendency to undergo hydrolysis decreases. Okay? But for these smaller ions of group 1 and group 2, the beryllium, okay? Beryllium, for instance, it can undergo hydrolysis. And so if you get a solution of beryllium, okay? If you get any soluble salt of beryllium, maybe beryllium nitrate, beryllium chloride, any soluble salt of beryllium, and you dissolve it in water. So instead of the pH to remain at 7, it will undergo hydrolysis, okay? And the salt become less than 7. The solution becomes acidic. That even if you dissolve sodium carbonate within that solution of beryllium, you'll be able to see effervescence of a colorless gas. Which gas? We are going to see. It's the question that I asked. So the carbonates and hydrogen carbonates of sodium and potassium, they can undergo hydrolysis to form an alkaline solution. And the salts that do contain a high charge density, they undergo hydrolysis. Okay? For instance, beryllium, it will undergo hydrolysis to form these ions, and then you release the hydrogen ions, which will make the solution to be slightly acidic. And I have a question that I'm supposed to discuss now, but I won't. It seems I'm kinda exhausted. So this is the question. I want you to go and do some reading about this. Make some research about this question. Okay? Explain what is observed when sodium carbonate, okay, is dissolved in a solution of beryllium chloride. So go and do some reading, go and make some research. Okay? And this question is the same as the other question. I say that I shall not discuss it now. So go and do some research, find out those equations, okay, how they are written till you come up with those equations of hydrolysis. Okay, yes, this is where we shall begin next time, I think on Monday. Okay, we shall finish, actually on Monday we shall finish S block elements and then see what we can